So in this video, we're going to prove the principle of inclusion-exclusion. And the idea is that given an element in one of these sets, we're going to count how many times it appears in one of these intersections with a positive sign and how many times it appears in the intersection with a negative sign, and prove that the two different counts are the same, so the positives and negatives cancel. And the basis of the proof is the fact that the binomial theorem is true. Right, x to the k, y to the n minus k. K goes from 0 up to n, and seeing what happens when you plug in -1 and 1. So we've already seen this depending on the lecture you've been attending, by pointing out that the number of subsets of even size is equal to the number of subsets of odd size. That's something we're going to take advantage in this proof. So recall the theorem: you're given a finite set x, another finite set I, and for each little element I in I, we have a subset AI of x. The way to think about it, and the terminology I'm going to use for the proof: x is the set of students, I is the set of clubs. And given a club, AI is the subset of students that are in that club. And so we're counting the number of students that are in no clubs. And the principle of inclusion-exclusion says the number of students that belong to no clubs to be computed by summing over, taking every subset of clubs, -1 to the size of that subset, at times the number of people that are at least those clubs, possibly more. So that's what this intersection represents. It's the subset of people who are in these clubs. So let's do the proof. The proof, we're going to start with the right-hand side. So we've got this summation over all subsets of clubs. Well, our Caveman Theorem is that we can replace this intersection with the sum over every element in this set of 1. Seems like a silly thing to do. Basically, I'm counting each person that's in this collection of clubs 1 by 1. Why would I do such a thing? Well, because I can bring this -1 to the s on the inside using the distributive property. And then I can combine these two summations together into 1. So I've got this alternating sum, and the summation is over all pairs x and s, where s is a subset of clubs and x is a member of at least these clubs. And this seems like a strange idea, but the point is I'm introducing the idea of summing over the members because we're about to change order of summation, and instead this counting says go over all subsets of the clubs, then count how many people are in at least those clubs. Now we're going to swap roles and say, given each student, figure out which clubs they are in. Namely, we're going to do the following. Instead of summing, so the first summation we summed over subsets first and then elements in the intersection. Instead, let's just sum over all people in the class and then sum over all subsets, just that that person belongs to at least the clubs in that subset. This is in fact equal. All I'm doing is changing the order of summation, really. So let's focus on this inner term. Fix an arbitrary person in the class. Let's say Melissa, for example's sake. Let's suppose, for example, that there are 3 clubs. Say the Combinatorics Club, the Statistics Club, and the Future Math Teachers Club. And Melissa belongs to the Combinatorics Club and the Statistics Club, but not the Future Math Teachers Club. So we see she's in A1 and A2, and therefore in the intersection, but she's not in A3. Therefore, since she's not in A3, she's definitely not in the intersection of A3 and A1, or A3 and A2, or the triple intersection. So what we see from this example is the following property. Melissa belongs to the clubs, given a subset of clubs, Melissa belongs to all those clubs to this intersection if and only if she's a member of each of those clubs in that subset. That's exactly what we're seeing here. Because she's not an element, she's not in the future math teachers club, she can't be in any intersection involving the future math teachers club. But because she's in the combinatorics club and the statistics club, she has to lie in the double intersection there. And so this is proof by example, but if you check the definition of intersection, this is a tautology. And so the point is, when she's not in one of these intersections, that's a term that doesn't pop up in this summation. So we only want to sum over subsets of I where she's actually in the intersection, and we see these subsets correspond to cases where she's in each element in the subset. In particular, S must be a subset of IX. What is IX? It's the clubs that Melissa belongs to. It's a set of clubs she isn't actually a member of. In this example, IX is 1 and 2. So our claim is X lies in this intersection of subsets if and only if this collection of subsets is a subset of IX. This is just a translation of this definition. And why would we want to do such a thing? Well, because this is a complicated formula. But this is a much easier one. So fixing our favorite person in the class, we now actually are just summing over all subsets of a given fixed set that is well defined. So let's apply that. This summation is now over all subsets of IX. Remember, if X is Melissa, IX are the clubs Melissa belongs to. Well, since we're summing over all subsets of a given finite set, another way to do this calculation, if you were to actually calculate it in real life, is to break subsets up by their sizes. We notice here that this alternating sum, this exponent, only depends on the size of S and nothing else. So rather than calculating exponentially many terms, we might as well calculate use binomial coefficients. What do I mean? Break this summation into two summations. First, sum over all possible sizes of subsets, then sum over all subsets of that size. Since that size is exactly k in this case, this size of S becomes replaced with k. Now what do we see? We see all the terms in this inner summation are constant. They all have the same value, -1 to the k. In particular, the Caveman Theorem says I can bring this -1 to the k on the outside. Now I'm just summing over all ones. By the Caveman Theorem, that's just the size of this set. And what is the size of this set? It's the binomial coefficient. Why? Because you're looking at all k subsets of a set of this set. And so the number of terms here is size of I of x, choose k. In other words, number of clubs Melissa belongs to, choosing k of those clubs. Why is this useful? Because by the binomial theorem, this is just -1 plus 1 to the power size of I of x. In other words, this complicated summation is really just -1 plus 1 to the number of clubs Melissa belongs to. Well, -1 plus 1 is 0. And we've covered 0 to a power in this class is 1 when Melissa doesn't belong to any clubs, which means that, so I'll stop there for right now. Otherwise, it's 0. So some of these terms are 0. So what that tells us is that in this summation, our terms are either 0 or they're 1. You're either in or you're out. When are you in this count? Well, when this I of x is empty. What was the definition of I of x? It's the clubs that x belongs to. So this is saying x belongs to no clubs, which means that x is not an element of AI for all I, which means x belongs to this set difference. On the other hand, when are you out? When is your contribution to the summation 0? When I of x is not empty, which means x actually belongs to at least one club. And that means x is actually in this union. And so the terms that are 0 are the terms when x is in the union, and the terms that are 1 is when x is not in the union. In particular, this summation reduces to this. These are the terms where it's 1. And the terms where it was 0 I just ignore because 0 never adds anything. Now by the Caveman Theorem, this is just the number of people that don't belong to any club. And there we have it, a proof that uses combinatorial reasoning and, in some sense, double counting. In this case, you could view it as double counting because the original formula involves first going over subsets of clubs and then going over members that are members of all those clubs simultaneously, whereas this second count involves first going over every person in the class and then summing over the clubs, subsets of clubs they belong to. This is not the only proof of the principle of inclusion-exclusion I know of. Every proof I know of at some point involves the binomial theorem. But in other proofs, you either use induction or algebra, or you use linear algebra. But for the purpose of this course, this one is self-contained and is using counting techniques from the course. And so if this seems mysterious, the whole idea is that basically, like we did with the 3 sets, you're assuming that you have size of I hands, and you're raising the hands up that correspond to the clubs you're members of, and I'm just doing this inclusion-exclusion count.